Imagine a localized explosion that is, well, hotter than the surface of the sun.
Oh, yeah. Literally vaporizing solid metal into molten shrapnel.
Right, and blasting it outward at over 700 miles per hour. And, we aren't talking about some military test site here. We're talking about a mechanic making, like, a fraction of an inch mistake while fixing your standard commuter car.
It completely shatters our standard perception of automotive repair. I mean, totally. Because when you pop the hood of a traditional combustion engine, the dangers are primarily mechanical.
Yeah, moving belts, hot exhaust manifolds.
Exactly. Things you can see and, actively avoid. But the modern electric vehicle introduces an entirely invisible, highly volatile chemical and electrical ecosystem.
Welcome to this deep dive. Today, we are looking past the sleek, silent dashboard of the modern EV, because for you to just get in and drive, an immense unseen infrastructure has to operate, well, flawlessly.
And we have some incredible documentation to pull from today to show you exactly how that works.
We do. We're sourcing from the official ASE high voltage electrical safety standards, the brand new version 2.1 for 2025, plus a 2026 buying guide for mobile EV chargers from ChargeRigs.
Right, and we're also looking at an industry report from DriveIs on AI's role in EV charging, a fascinating academic paper from JFR on hybrid solar-powered wireless charging vans, and a recent announcement from L-Charge about their new 60-kilowatt mobile charging vehicle.
It's a lot of ground to cover, but our mission today is really to uncover the extreme safety protocols required just to touch these vehicles, the mobile off-grid infrastructure being deployed to keep them moving, and the artificial intelligence operating constantly in the background to prevent the neighborhood power grid from just buckling under the strain.
To really grasp the scale of this ecosystem, we have to start at the individual vehicle level. Because before we talk about charging them, we need to understand what's inside them.
The power is just massive.
It is. The baseline power architectures for consumer electric vehicles right now operate anywhere from 400 to 800 volts of direct current. And in the commercial sector, like heavy-duty trucks and transit buses, those systems are routinely exceeding 1,200 volts.
Okay, let's unpack this, because the physiological reality of those numbers is terrifying. Humans are, notoriously bad at intuitively understanding electricity.
We really are.
We hear 800 volts, and we just know it's a lot. But I was reading through those 2025 ASE high-voltage standards, and it makes you view an EV mechanic less like a traditional wrench turner and more like a bomb defusal expert handling live ordnance.
That's a very accurate comparison. The ASE manual is incredibly uncompromising on this point, specifically regarding the biological mechanics of a shock hazard.
Right, because everyone thinks the voltage is what kills you.
Yeah, that's the prevailing myth.
Hmm.
High voltage is dangerous, sure, but voltage is merely the pressure pushing the electricity. The current, which we measure in amps or milliamps, is what actually inflicts the physiological damage.
Because the human body essentially just acts as a resistor within that electrical circuit, right?
Exactly. The human nervous system already operates on tiny electrical impulses. So when an external current enters the body, it violently overrides those internal signals. Look at the let-go threshold.
Which is how much current it takes for your muscles to just lock up.
Yes. At an exposure of just 6 to 16 milliamps, which is an infinitesimally small fraction of a single amp, your muscles involuntarily contract and lock.
Oh, wow.
So if a technician is holding a live battery terminal and hits that threshold, their hand clamps shut. They literally lose the biomechanical ability to let go of the power source.
So they are just frozen to the battery, and if that current continues to climb and crosses the chest, I read it only takes about 75 milliamps to throw the heart into ventricular fibrillation.
Which is almost immediately lethal. The variable here, the thing that saves or kills you, is the skin's resistance. Dry, intact human skin actually provides a decent barrier.
It's like 1,000 to 100,000 ohms of electrical resistance, right?
Correct. But the terrifying drop-off occurs if the skin is compromised. If a technician is sweating, or, more grimly, if the initial shock creates a burn that destroys the epidermis, that resistance plummets exponentially.
The ASE standards run the math on that exact scenario, and it's sobering. If someone touches a 400-volt source and their skin resistance drops to 600 ohms due to, sweat or an injury, the resulting current flowing through their body is 660 milliamps.
Yeah.
That is nearly 9 times the lethal limit.
It's instant.
Yeah.
And electrocution is only one half of the high-voltage threat matrix. The other is the arc flash.
Which is just nightmare fuel.
It really is. This happens when the insulation or the physical air gap between high-voltage conductors fails. The electricity essentially tears through the air, ionizing it and creating a plasma arc.
Which brings us back to that 35,000 degree Fahrenheit explosion we mentioned at the start.
Right, roughly 19,500 degrees Celsius. At that thermal extreme, the copper and aluminum conductors don't just melt. They undergo a rapid phase change and completely vaporize.
And when metal turns into a gas instantly, it expands, right?
Violently. This extreme expansion expels molten metal outward at 740 miles per hour. And it's accompanied by blinding ultraviolet light and a massive thermoacoustic shock wave.
I was looking at the diagnostic tools used around this equipment, and the paranoia built into the protocol is actually brilliant. I mean, you can't just probe an 800-volt circuit with a standard hardware store multimeter.
No, absolutely not.
If the circuit faults, the tool itself could literally vaporize in your hands.
That's why technicians are mandated to use heavily shielded tools rated at Cat 3 1000V or CCAT 4 600V. These aren't just wrapped in thick plastic. They contain specialized high-energy fuses inside the housing.
So if a surge hits, the fuse takes the hit.
Exactly. If an unexpected power surge hits the meter, those internal fuses are engineered to physically contain the explosive energy of a short circuit. It prevents the blast from breaching the casing and taking off the technician's hand.
But the testing procedure for those tools is what really stood out to me. The ASE manual details the use of these things called proving units.
Oh, the live-dead-live verification loop.
Yes. Before a mechanic even touches the EV, they hook their multimeter up to this pocket-sized device that generates a known stable voltage. They test the meter to prove the tool is functioning. Then they test the car to prove the massive battery is successfully de-energized.
Like making sure it's dead.
And then, this is the crazy part, they test the proving unit again to mathematically prove their meter didn't secretly break while they were testing the car. It's so intense.
And that same level of rigorous paranoia applies to the personal protective equipment, too. The baseline defense is a pair of Class 0 electrically insulating rubber gloves.
But rubber naturally degrades over time.
It does. So before every single shift, the technician must use a pneumatic pump to inflate the gloves like a balloon. They're checking for microscopic air leaks. A pinhole invisible to the naked eye is a wide-open door for an electrical current.
And then they wear leather over those, right?
Yes. Heavy leather overgloves are worn on top to prevent mechanical tears from sharp metal edges under the hood. Pair that with an arc flash-rated face shield, and, the physical preparation is exhausting before a single bolt is turned.
There's also the one-hand rule, which feels incredibly counterintuitive until you understand the biology.
Yeah, keeping one hand in your pocket.
Right. When probing a live high-voltage circuit, mechanics are trained to keep one hand firmly behind their back or in their pocket.
The logic there is purely anatomical. If you touch a live wire with one hand, the current might travel down your leg and out through your boots into the ground, which causes severe burns, obviously, but might spare your vital organs.
But if you use two hands?
Right, say one hand on the live conductor and the other hand leaning on the metal chassis of the car for balance, you've just created a perfect bridge. The electricity takes the path of least resistance directly across your chest, passing straight through your heart.
Wow. So taking that second hand out of the equation physically breaks that deadly circuit path.
Precisely. It's a lifesaver.
So, if a single vehicle contains enough volatile energy to vaporize metal and requires this level of extreme protocol just to safely run a diagnostic test, scaling that up to a fleet level poses a massive logistical nightmare.
A huge one.
You can't just plug 50 of these rolling power plants into a standard event space grid or an older building's infrastructure, which is why the industry is suddenly pivoting toward mobile external power.
We are seeing a rapid uncoupling from the traditional stationary grid. The 2026 buying guide from Charge Rigs highlights the necessity of this shift really well.
Because building permanent chargers takes forever.
Exactly. When infrastructure development requires trenching concrete, laying heavy-gauge copper wire, and waiting sometimes years for municipal utility permits, the deployment bottleneck becomes insurmountable.
So instead of bringing the car to the power plant, we are bringing a localized power plant to the car.
That's the idea. The Charge Rigs FLIEXX system illustrates the scale of the solution perfectly. It is a massive 120 kilowatt battery-powered mobile DC fast charger.
You just tow it in?
Yeah, you tow it into a parking lot or a field, level it out, and it's dispensing power in an hour. Because the system is entirely self-contained, simply discharging its own internal battery into the vehicle's battery, there are zero localized emissions and no engine noise.
Which means you can roll an industrial-scale fast charger indoors at a convention center or a pop-up event, completely bypassing the local utility grid.
And if you are running a multi-day festival where a pure battery unit would run dry, the guide notes they have diesel generator alternatives like the GenEQ to
Yeah.
provide continuous runtime.
We're seeing intense competition in this space, too, with companies like L-Charge announcing new 60-kilowatt mobile charging vehicles designed specifically as an on-demand rapid response utility. It's like calling an Uber, but for electricity.
It is. And the academic sector is pushing this even further. A recent paper in the JFR, the Journal of Autonomous and Alternative Fuel Research, details working prototypes for hybrid solar-powered wireless EV charging vans.
Okay, here's where it gets really
That
interesting.
was wild.
A van covered in solar photovoltaic panels, generating clean energy, storing it in an internal battery bank, and then transferring that energy into a parked EV without a single physical cable being plugged in.
Complete severing from physical infrastructure.
They use wireless power transfer, or WPT.
Uh-huh.
I like to think of this using a tuning fork analogy.
That's actually an excellent way to visualize the physics.
Because if you strike a tuning fork, it vibrates at a highly specific frequency. And if you place another identical tuning fork nearby, the sound waves will actually cause the second one to start vibrating in harmony without them ever touching.
Right, and WPT uses inductive and resonant magnetic coupling to do the exact same thing with electricity.
So the pad underneath the van generates an oscillating magnetic field at a specific frequency, and the receiver pad underneath the EV catches that magnetic wave and converts it back into direct current to charge the battery.
Exactly. And the elimination of physical cables removes almost all of the safety hazards we analyzed in the ASE manual.
Because there's nothing to touch.
Right. There are no high-voltage connectors to degrade over time, no risk of physical exposure to the conductors, and no arc flash potential at the connection point, because the energy is transferred as a magnetic field across a physical air gap.
Okay, wait. I have to push back here.
Sure.
If wireless charging completely eliminates the high-voltage cable danger and is vastly more convenient for the driver, why are we still wasting time with physical plugs? Why hasn't the entire automotive industry just moved to wireless overnight?
It comes down to the unforgiving physics of energy transfer efficiency. The JAFR paper validates the safety benefits, absolutely, but it highlights the inherent mechanical flaw in magnetic coupling.
Which is what? Alignment.
Yes. For WPT to operate at peak efficiency, the transmitter coil in the ground and the receiver coil in the car must be perfectly aligned.
So if a driver parks slightly off-center,
The efficiency plummets. If those coils are misaligned by just a few inches, or if the vehicle sits too high and the air gap is too large, a significant portion of the magnetic field fails to interact with the receiver pad.
and that energy just goes nowhere.
Well, that untethered energy doesn't just disappear. It is lost as ambient heat. Because of this efficiency drop, wireless charging universally results in slower charging times compared to a direct physical wired connection.
Ah, I see.
So for a solar-powered van doing a top-up on the street, the convenience outweighs the speed loss. But for a highway rest stop, where a driver wants maximum power transfer in 15 minutes, physical copper still reigns supreme.
Even with these mobile solutions filling the gaps, the raw scale of this ecosystem is on a collision course with the physical limits of our power grid. I was reading an industry report from Drives, and it maps out this bottleneck clearly.
It's a massive issue.
By 2025, global EV sales crossed 22 million units, supported by over 5 million public chargers. That is a staggering amount of power being drawn.
It really is. The Drives report notes that over 90% of charging network operators now cite local grid capacity as the primary barrier to expansion.
Because everyone charges at the same time.
Exactly. When millions of drivers return home at 6:20 p.m. and plug-in vehicles demanding essentially the same power draw as a small house, the localized strain on neighborhood transformers is catastrophic.
We just don't have the copper for it.
We cannot physically mine, manufacture, and lay enough copper wire to upgrade the grid at the speed required to handle that.
So the solution isn't physical infrastructure, it's the invisible conductor operating behind the scenes, artificial intelligence.
The entire system would collapse without it. AI is fundamentally changing how energy is distributed and priced. The historical model of fixed electricity pricing is functionally dead in this sector.
Right, because if an operator charges a flat rate, human behavior dictates everyone will charge at the most convenient time.
Creating massive, unsustainable demand spikes.
And during those peak spikes, the wholesale cost of electricity skyrockets, meaning the station operator actually loses money on every kilowatt they dispense. So AI introduces dynamic pricing.
And the scale of the data processing is staggering. The DriveHiz algorithms analyze over 240 distinct data fields in real time.
Wait, 240?
Yes. They aren't just looking at the car plugged into the stall. They are monitoring the real-time load on the regional utility grid, fluctuating wholesale energy markets, incoming weather patterns that might affect solar generation.
Oh, because if it's cloudy, solar drops and prices go up.
Precisely. They even analyze the exact pricing of a competitor's charging station 2 miles down the road.
And it uses all of that data to manipulate the cost minute by minute to actively steer human behavior.
And the data proves it works. The report highlights that implementing a 40% price reduction during deep off-peak hours, say 3:20 a.m., when wind farms are producing excess power and grid demand, is at its lowest can boost charger utilization by 117%.
So the AI effectively bribes drivers to charge when the grid has an abundance of energy.
Exactly, completely flattening the demand curve.
That solves the macro grid problem, but AI is also tackling the most infuriating micro problem for drivers: broken chargers. I mean, there is nothing worse than pulling up with a 2% battery and finding a dead screen.
It's the worst. And the industry failure rate hovered around 14%, meaning roughly 1 in 7 charging sessions failed. But AI attacks this through predictive maintenance.
How does that work? Does it just know when it's going to break?
Kind of, yeah. When a charger is functioning normally, the software is constantly monitoring microfluctuations in power delivery, tracking internal temperature variances, and measuring the electrical resistance at the connector pin.
Oh, because as you plug and unplug a massive cable thousands of times, the metal contacts physically wear down, increasing the resistance.
And increased resistance generates heat. The AI detects these microscopic electrical signatures of a failing component days or even weeks before it completely gives out.
So they fix it before we even get there.
Exactly. It shifts the entire maintenance paradigm from reactive emergency repairs to proactive scheduled service. A technician can swap a degrading cable at 4:00 a.m. on a Tuesday, completely avoiding a catastrophic failure during the Friday rush hour.
But the financial centerpiece of this AI network is what Drivez calls smart energy management, which is specifically designed to avoid demand charges.
Commercial electricity billing is brutal.
Yeah, utility companies often bill a business based on their single highest peak of power draw during a 15-minute window for the entire month, right?
Right, so if a charging hub operates 10 fast chargers and 10 vehicles plug in simultaneously at maximum capacity, that momentary spike in demand could trigger utility fees in the tens of thousands of dollars.
Just wiping out the station's profit for the quarter in 15 minutes.
Exactly. So the AI orchestrates the entire site. It coordinates local solar panels, draws from on-site stationary battery storage, and even utilizes vehicle-to-grid or V2G technology to supplement the power demand. It completely shields the local grid from that massive spike.
Okay, so what does this all mean? When you plug your vehicle in, you are surrendering control to that algorithm. Wait, does this mean the AI is intentionally throttling my charging speed just to save the operator money on a demand charge? Like, am I sitting there for an extra 20 minutes because an algorithm decided the local grid was stressed?
Yes, the power delivery is actively modulated. However, what's fascinating here is that the ecosystem turns what sounds like a negative into a highly choreographed exchange of energy.
How so?
The station's AI isn't operating in a vacuum. It establishes a secure communication handshake with your specific vehicle's internal software.
Oh, so it accesses my battery state of charge and my active route planning.
Yes. It knows exactly how much power you currently have, the degradation health of your specific battery cells, and how many miles you need to reach your inputted destination.
Okay, that makes sense.
If it knows you only need 40 miles of range to get home, and you plan to be parked for 45 minutes eating lunch, it will not slam your battery with 150 kilowatts of peak power during a grid stress event.
Because it knows I don't need it right that second.
Right. It trips exactly the power you need, precisely when you need it. Charging transitions from a brute force transaction into a hyper-intelligent, dynamic conversation between the grid and the vehicle.
That is a staggering paradigm shift. The layers of complexity we've peeled back today are incredible. For you listening, the next time you see an EV glide silently past you, or you plug one in yourself, you'll know there is a profound depth to the infrastructure making that possible.
So much more than just a plug and a battery.
Exactly. You'll picture the mechanics relying on pneumatic air leak tests and the one-hand rule just to survive working near 800-volt circuits. You'll visualize the mobile solar vans using resonant magnetic frequencies to beam power through the air. And you'll know that behind every successful road trip, And artificial intelligence is crunching 240 variables a second, actively manipulating prices and orchestrating power flows to ensure the power grid doesn't collapse under our collective demand.
It is a phenomenal achievement in engineering and software.
Yeah.
But, mapping out this deeply interconnected ecosystem raises one final, highly concerning vulnerability.
What's that?
We explored how AI manages these massive hubs, specifically utilizing that vehicle-to-grid technology where cars can actively discharge their stored power back into the grid to stabilize it.
Right.
By the end of the decade, we will have tens of millions of EVs on the road. They are essentially massive rolling high-voltage batteries, permanently connected to a centralized grid, with their charging and discharging behavior actively dictated by cloud-based AI algorithms.
Yeah, that's a whole system.
Well, if that central AI network is manipulated or hacked, could a coordinated cyber attack bypass the safety protocols and trick a localized fleet of 50,000 EVs into discharging their massive battery packs back into the local grid at exactly the same microsecond?
Oh, wow.
We wouldn't just be looking at a software glitch. We could be effectively weaponizing our own vehicles to crash the neighborhood power grid from the inside out. Something to think about on your next commute.